Hello, my name is Mohammad Sadri and I'm a postdoctoral researcher at Microelectronics System Design Research Group at TU Kaiserslautern. In this video today I am trying to briefly answer this question: what is Xilinx ZYNQ? This video is a part of a complete series of educational videos that we are creating here at TU Kaiserslautern regarding the ZYNQ device and designing embedded systems using Xilinx ZYNQ. So, in this video, I am going to have a brief introduction on what is heterogeneous computing, what does it mean. Then I will have a brief overview on the Xilinx ZYNQ architecture, and then finally I will have a brief overview on available Xilinx ZYNQ devices, their price, and the boards, the evaluation kits which are developed for this device at the moment. 1951. There was UNIVAC 1 computer which was capable of performing 0.015 operations consuming 1 watt-second energy. And then half a century later, at 2012, we see devices like ST P2012 chip which is capable of performing 40 billion operations per consuming 1 watt-second. So, during time, what has happened, the performance per watt is improved. In fact, the challenge has been to perform more and more computations, consuming less and less power. One good solution to achieve this goal is specialized hardware units. In fact, as we have a computational task, instead of running the whole task using one or several CPU cores, we look at the task and we see if there exists the potential of accelerating different parts of this computational task using specialized hardware units. Indeed, units which are only and only designed to perform a specific calculation or computation. This way, for those computations, we can perform them in a smaller amount of time, consuming less total power. So, suppose that we have a normal CPU subsystem. Our CPU has a very simple cache, and then there is the DRAM memory, and then there are a set of tasks that the CPU is executing. These tasks have dependencies on the variables. The variables are stored either in the DRAM memory or some of them are cached into the caches of the CPU. Now, I may introduce some specialized hardware units that I call accelerators, capable of executing some or parts of these tasks, and I may offload the computational tasks from the CPU to the hardware accelerator. This way, I will be able to do my executions with better performance per watt and in a shorter period of time. But it is not necessarily that easy. The point is, there are lots of problems that can happen by offloading these tasks to the accelerators. For example, these tasks need to have access to variables to perform their operation. So the accelerators should be able to access the DRAM memory to read the variables and then to write the results back to the DRAM memory. But, for example, look at variable 2. Variable 2 is also cached in the CPU caches. So, where the accelerator should really look for variable 2? Inside the DRAM or inside the caches? This is a major problem. Or, suppose that the accelerator wants to read the variables from the DRAM memory. How should the accelerator obtain the addresses of these variables? The point is, as we know, the CPUs are usually executing their tasks, their applications in virtual address space. In fact, we have an MMU which is active, and the applications that we are running, the arrays that we are allocating, they are all using virtual addresses. While on the other hand, the accelerators, they are using the physical addresses. So whenever the CPU wants to offload a task to the accelerator, it should also perform the conversion from virtual to physical addresses. If the arrays, if the data elements which are passed to the accelerator are simple, this conversion doesn't take time and is straightforward and is easy. While if the CPU is passing a complicated data structure to the accelerator, then it can be a major problem. There are other problems which can happen by offloading tasks to the accelerators. So while this new idea, or this idea in general, can give us a lot of advantages, it brings us at the same time some design challenges. Okay, if we look at the digital hardware architecture developed for processing, basically we can divide them into two categories: the heterogeneous computing platforms and the homogeneous computing platforms. In a homogeneous computing platform, you have an architecture in which all of your processing elements are of the same type. Here is an example. This is a block diagram of Intel SCC, Intel Single Chip Cloud Computer. It contains 24 processing tiles. Each tile, as you see, contains 2 Intel Pentium CPU cores. Total 48 Intel Pentium CPU cores, but they are all the same type. Here is an example of a heterogeneous computing platform. This is Texas Instruments Keystone 2 architecture. Obviously, this is one part of the architecture, but the most important part. As you see, this architecture contains computing elements which are not of the same type. It contains 4 ARM A15 CPU cores and then 8 66X DSP cores. These two computational elements are different and they will be used for different computational tasks. So as there is a computational task, for example, an FIR filter, something which is really related to signal processing, then the task will be executed by the DSP cores. While if you have a, for example, general purpose task, like you are bringing up the Linux operating system, or you are doing a kind of a scheduling between tasks in the system, or you are managing some kind of interface to the real world, then the ARM CPU cores will be used. As you see, we have specialized units that will be used for tasks according to the type of work that they are going to execute. So the point is, for some processing tasks, FPGAs are really suitable. For some others, not. For example, if you have a very large flow of data which comes into your system, gets processed, and then goes out of your system, then usually FPGA is a very nice choice. For example, if you need to perform, for example, fast Fourier transform, FFT, calculations on the incoming samples from an A to D, a high-speed A to D, then maybe the FPGA is a really nice choice because it can perform for you a specific ensemble of simple calculations with a very high speed. So if you have algorithms which are massively parallel, Or if you have applications in which you need a very large number of IOs, then FPGAs are really a nice choice. But for some applications, FPGAs really, they don't fit into the problem very well. For example, when you have an application in which every time that the data arrives, based on the data, based on the values, you should do a different task, or you should perform complicated decision making, or you should run a complicated algorithm which contains a lot of for loops and ifs and if then else and this kind of control, flow control operations, then maybe an FPGA is not really a suitable choice. Indeed, if you want to implement that kind of algorithm with the FPGA, you will end up a very large state machine, which when you eventually implement on the hardware, first, it has a lot of bugs and problems which you should solve, and it takes a lot of time for you from your time. And then second, it doesn't give you really a good performance. So a CPU is really a nice choice for these kind of applications. The point is, in many times, we really require to have both of the functionalities in parallel. I mean, if we look at the entire project that we are doing, in some parts of this project, we need very high processing power, and we have massively parallel algorithms. And on some other parts, we have very complicated decision making. Indeed, the hardware that I am going to develop for this project should contain both parts. I need the FPGA, and also I need the CPU. Okay, one solution is, since FPGA is providing us a sea of gates and we can realize any kind of hardware using FPGA, one solution is we implement our CPU core as a part of FPGA logic. But practice has shown that this idea, many times, it doesn't really work very well. Because as soon as you implement the CPU on the FPGA logic, first, you are consuming a very large amount of FPGA logic for your CPU. Second, the CPU is not giving you really high performance. As an example, for the Xilinx Microblade Soft CPU core, if you have experience designing with the Microblades, you have seen that you will be really, really happy if the Microblades reach an operating clock frequency of 125 MHz. But it's really bulky, big, and slow. We can put the FPGA component beside our CPU component, and whenever we need, the data will be passed on the PCB from the FPGA to the CPU, and then it will come back. This solution needs usually a PCB which is complicated, because instead of one FPGA component, for example, you are placing two. And then there will be latencies from the FPGA to CPU for these two to talk to each other, and this can result in many other problems. So what has happened during time? The thing has happened is that the FPGA makers companies, they have tried to integrate the CPU core itself as a hard IP block, as a hard component into the heart of the FPGA. Here is an example. This is a simple block diagram of Xilinx Virtex 5 FX FPGA. As you see, at the heart of this FPGA, we have the PowerPC 440 CPU core running as a hard IP component. This allows the component to run at very high frequencies. For example, it can operate at 400 or 500 MHz, and it can give you a very high processing power, while at the same time it is not consuming the configurable resources of the FPGA. So in its Virtex 5 FX series, Xilinx is providing the users a complete PowerPC subsystem which is capable of doing a large amount of processing. So you divide your algorithm between the programmable logic and between the PowerPC. Now, another example in which you can see that inside an FPGA we have a CPU subsystem is the Xilinx ZYNQ. Here is a block diagram of the Xilinx ZYNQ. The Xilinx ZYNQ is divided into two parts, the PS and the PL. The PL is roughly an FPGA, similar to the other FPGAs that we have seen before. The PS is new. The PL stands for programmable logic. The PS stands for programmable system. The programmable system contains an ARM CPU subsystem, which is based on ARM Cortex A9 MP core. So you have two ARM Cortex A9 MP core CPUs there. And each of these CPUs has its own specific level 1 caches. Then there is the shared L2 cache, which has a size of 512 kilobytes. And then between these, we have the Snoop control unit. What is the Snoop control unit? It is responsible for maintaining coherency between the contents of the level 1 caches of the two CPUs, as well as the level 2 cache and the level 1 caches. For example, if your both CPU cores are running a task and the first CPU core is fetching a variable, is updating that variable, and instead of writing back that variable, keeps the variable into its local cache, if the next CPU is going to use the same variable, the Snoop control unit looks and understands that the first CPU has changed this variable, so it invalidates the entry of that variable from the caches of the second CPU, and it makes the first CPU to also write back that variable to the DRAM memory so that the contents of the caches be completely coherent. Then, the programmable system contains many other components. It contains one DDR3 DRAM controller and also a bunch of peripherals like UART, USB, network interface, gigabit Ethernet, SD card, and GPIO interfaces. It contains an internal DMA controller and also an interconnect which connects all of these guys together. There exists also a 256 kilobytes on-chip memory on the PS. Then, through this interconnect, we have a set of AXI interfaces that provide the required interface for the logic resided in the programmable logic part, in the FPGA part, to talk and to transfer data to the programmable system. Here, what I am showing you are 4 high-performance AXI slave interfaces. These high-performance AXI slave interfaces will be driven by the AXI masters that you develop inside the FPGA part of the ZYNQ. You may ask yourself, what is AXI? If you don't know what is AXI, you can simply search, for example, in YouTube, what is AXI, and you will have your answer through the other videos that we have produced. The Xilinx ZYNQ also contains another set of AXI slave interfaces for the AXI masters on the programmable logic to drive and to initiate transactions to the address space of the ARM CPU cores. Then there are a set of AXI master interfaces through which the CPU cores and the logic resided on the PS can initiate AXI transactions to the AXI slaves that you develop on the programmable logic part of the ZYNQ device. So you implement your AXI slaves and you connect them to each of GP0 or GP1 ports, and then your ARM CPU cores can initiate read or write transactions to each of these AXI slave interfaces. And finally, we have the accelerator coherency port through which the AXI masters resided on the programmable logic part of the ZYNQ device can initiate read and write transactions to the address space of the ARM CPUs. So the accelerator coherency port is an AXI slave port, and the transactions which happen through this port are happening in full coherence with the caches of the CPU cores. What does that mean? So, through this example, I'm trying to show you what is happening really on the ACP port. Suppose that we have our simple CPU subsystem, and then we have the hardware accelerators. And then there are a set of tasks which are offloaded to the hardware accelerators. For example, task 2 and task 4. And then the point is, these tasks need to have access to some variables inside the shared memory to perform their operation. But these variables may have been cached by the CPU. For example, variable 2 is cached right now by the CPU, and there may exist one newer instance of variable 2 inside the cache, which is not necessarily the same as the instance that we have inside the DRAM. So if we want to perform a correct operation every time that the task 4 wants to read variable 2, we should first make the CPU to flush the cache completely to the DRAM memory, so that we can be sure that the latest version of variable 2 is right now in the DRAM memory, and the accelerator is reading the correct value. But what accelerator coherency port allows you to do, in fact, the accelerator coherency port allows the accelerator to have access to the contents of the cache directly. So the accelerator, instead of going to the DRAM to read variable 2, it goes directly to the caches of the CPU. And if variable 2 is inside the cache, it will directly read the latest version of variable 2. But if it doesn't exist inside the cache, and the accelerator has performed a transaction, a read transaction through the ACP port to the CPU subsystem, then the variable will be read from the DRAM and then will be transferred to the ACP port and then to the accelerator. So when the accelerator is performing all of the transactions through the accelerated coherency port, it is sure that it is always reading the latest version of the variable, considering the cached variables and those who has been changed by the CPU. This allows the accelerator and the CPU to efficiently cooperate with each other in computational tasks, and it provides us the possibility of improving performance of calculations when the CPU and the accelerator cooperate on a computational task, and also it will improve total power consumption. When you go to the market, there are a set of different options for the Xilinx ZYNQ device when you want to purchase one. Here is one important option, and that is the speed grade of the device. Based on the quality of the final fabricated ZYNQ device in the silicon fab, the company divides the ZYNQ devices into three categories and marks each category with a different speed grade. And each device with a different speed grade is capable of running at different clock frequency. So the maximum running clock frequency of the device is indicated somehow by the speed grade of the device. For example, here for the Xilinx ZYNQ device, we have three speed grades: -1, -2, -3. The one with -3 is the fastest ZYNQ device that you can buy, but it is the most expensive. Then the next one, -2, and the slowest one, -1. And the -1 is the cheapest device. So, how are the speeds? The ARM CPU subsystem in the -1 device can operate up to 667 MHz, while for the -3 it goes over 800. And if you implement a 64-bit counter on the PL of the Xilinx ZYNQ device, and then you run the synthesis and implementation flow, and you perform static timing analysis, you can see that your 64-bit counter for a -1 speed grade device can operate, based on the report of the tool, can operate up to 277 MHz, while for the -3 speed grade device, it can go up to 370. Usually for many projects, we prefer to pay less money and to try to optimize the speed of our design so that we can keep the delays in different parts of the pipelines as low as possible, so that we can run our design at the highest possible clock frequency while paying the smallest amount of money. These numbers are the ones reported by the datasheet and the tool, and maybe in practice, if you even design a 64-bit counter and you implement it on a -1 speed grade device, and then you push the device to, for example, 300, 320, maybe it works, but there is no guarantee. And usually you don't want to do something which is not guaranteed. Here, I am listing indeed the Xilinx ZYNQ devices. So we have the first device. It is XC7Z010, and then the next device is here, XC7Z020, then 030, 045, and 100. And in the second row, I'm listing, in fact, the prices for these devices. The smallest price that I found in DigiKey at the time of this presentation, you can see this $54 for the smallest ZYNQ device. Then for the next one is 119, 200, 1000, and I didn't find any price for the biggest Xilinx ZYNQ device. As you see, the Xilinx ZYNQ devices, they are very expensive. Generally, FPGAs are expensive. For example, in the red, I am showing you the prices for Xilinx Spartan 6 devices. This is XC6 SLX45, then SLX100, SLX150. And this number, price 52, 129, 195. As you see, the device is really expensive. The point is, when you want to select the device for your project, you should select the device that you really need. So you don't pay money for something that you are not going to use. For example, here what I see that if we forget about the processing system of the ZYNQ, suppose that we have a project in which we are involved only and only with the programmable logic, with the programmable fabric, with the FPGA. And in this project, we don't want to do anything with the ARM cores. We don't have any CPU. Then there is no reason for you to choose the ZYNQ device. Why? Because if you choose this Spartan 6 device, the SLX 45, you are paying $52, and in front of this $52, you are receiving 43 kilo logic cells. While at the same time here for the Xilinx ZYNQ device, I am paying $54 and I am only receiving 28 kilo logic cells. So as you see, if I am going to only and only implement my circuit using the logic cells, then it doesn't make sense to go for the ZYNQ device. Then there exists a very large number of evaluation boards for the Xilinx ZYNQ device. I have listed some of them here, which are right now available in the market. The ZC702, Z-board, ZC706. The Z-board is from zboard.org, I would say, or I can say from Avnet. The ZC702, ZC706, they are from in fact Xilinx itself, and then we have the Zybo is Digilent, and then there are a set of German companies, they are producing the ZYNQ device, and then there are some interesting ZYNQ boards such as Red Pitaya, which contains the A2D D2A high-speed A2D D2As along with the ZYNQ device itself. So we had a very brief overview on the Xilinx ZYNQ, and this was the first video. I will continue, in fact, this overview, and I will repeat what I said today during the rest of the videos many times. So if you didn't get some parts of the descriptions, that is no matter, it's not important, because it's something that we will repeat several times, each of these parts of this system. We come to the end of this video. Thanks for watching, and you can follow us through the other videos that we will create soon.